Okay, last time at the end of the lecture, we talked about making a top-down description of a quantum order, and we derived very quickly an equation for the macroscopic wave function in space and time for a condensate describing quantum Bose order. And the way we did it was very simple. We just simply said that you have a Schrödinger equation. The particles are moving in a potential. That potential is basically the energy of interaction times the density of the particles. So then it becomes something that looks like this. Just the energy times the density, and the density is psi squared. And so we ended up with an equation which we call the nonlinear Schrödinger equation, which, and in the context of superfluidity, it's known as the Gross-Pitievsky equation. This equation, by the way, is very, very highly studied. There must be thousands of papers that study this equation. This equation comes up if you're trying to look at the theory of quantum optics. It comes up if you're trying to look at lasers. It comes up in a number of other contexts. It has lots of very remarkable properties, and we're going to go and look at some of those today. So this is the way that we can use a sort of Landau theory type continuum description of quantum order, where we've coarse-grained on a large scale. And what I'm going to do today is I'm going to begin by talking about the Gross-Pitievsky equation, and I'm going to show you how we can use it to describe the structure of a quantum vortex. So I'm going to show you how we do that, and then I'm going to show you at the end of that we can make that description self-consistent. In other words, we can verify that, at least within the assumptions of the theory, that what we assumed to be the case, and I'll tell you what I mean by that in terms of density and so on, the weak interactions of the bosons, actually the theory predicts that it is in the weak limit. So I'm going to introduce you to this very important idea of self-consistency. Self-consistency means if I make a theory with a certain assumptions, then I do a calculation and calculate something, then I make a prediction based on those assumptions. I should be able to go back and close the loop and check, does the predictions of the theory violate the assumptions of the theory? If it violates the assumptions of the theory, it's not a self-consistent theory. So I'm going to show you that this theory is self-consistent. We'll get to that in a few minutes. That's where I'm going to end this section on quantum order, condensed matter. And then we're going to talk about non-equilibrium pattern formation, and we'll get started on that with talking about thermal convection. So without further ado, hopefully no apps decide to update themselves again during the lecture. So let's start off by talking about the quantum vortex line solution of the Gross-Pitievsky equation. So this is in my notes, emergent states of matter notes that you have on the Canvas website, section 3.7.4. And what we're going to do is this. What we want to do is say, let's suppose I have a quantum vortex that is is going up the z-axis. The system is rotating, creating this vortex. We talked about that last time. And I want to know what its spatial profile looks like. How does the order parameter vary as I go through that quantum vortex? We've talked about the vortex as representing a topological defect. So now we want to see, is this vortex really a defect at all, and in what sense it is? So let's get started on that. So we're going to be thinking about the weakly interacting Bose gas. So weak interactions in the same way that we did in very elementary statistical mechanics. First of all, you started off with ideal particles that never interact. And then hopefully some of you have done this where you start putting in weak interactions, and then you learn how to do diagrammatic perturbation theory and construct the many-body equations of state for an interacting gas. How many people here have done that? You did. Okay, one. Okay, so clearly I need to volunteer to teach statistical mechanics in this university. But anyway, we'll talk about the quantum version of that in a minute, and then we're going to be doing this at zero temperature. Okay, so let's go back to where we started. So we started with the time dependent Gross-Pitievsky equation, which I'm showing you over here on the right-hand side, and And so this is like the Schrödinger equation, but with this potential that goes like U naught psi squared. And U naught is the strength of the interactions. So this is the parameter that we called U naught last time. Now, when you have when you remember from elementary quantum mechanics, if you want to work out the stationary states, what you do is you solve the problem where the wave function is now a product of a spatially dependent part and a time-dependent part, and that time-dependent part just rotates its phase by an amount that goes like e to the I times the energy times time over Planck's constant. So we're going to do the same thing over here. We're going to write we're going to write the phase as e to the I times a variable mu, which I will tell you what that is in a minute, times t over h bar, and then multiplied by a spatially dependent function psi naught. And so we've factored out the spatial dependence and the time dependence. So if you now plug this in to the Gross-Pitievsky equation, now you get the time-independent Gross-Pitievsky equation. It's the exact analog of the time-independent Schrödinger equation from the time-dependent Schrödinger equation. Okay, now the thing that we want to do is we want to work out the behavior of a quantum vortex. So what we're looking at is a quantum vortex line that is rotating about the z-axis. The vortex line is in pink, going up the z-axis. And I'm going to be using cylindrical polar coordinates. So I have a radial vector r, a radial coordinate r, and a phi dependent, an angle phi, and then the z variable going up in the z direction. So that's the geometry. Now, psi naught squared is equal to the number density of the particles in the ground state, which I've called n naught, which is basically n naught divided by v as usual. And I'm going to show you that this variable n naught is from that I can derive what the chemical potential is. So this variable this variable mu that we have over here, this variable mu is going to actually end up being the chemical potential, and it's going to have this value. And I'm going to show you that on the next screen. So that is our setup. So, and the last thing is we're at low temperatures. So if there were no interactions, all the particles would be in the ground state. You'd have a complete Bose-Einstein condensate. But we have some interactions. So because there are some interactions, some of the particles, a small number, are going to be in excited states. The number that's going to be in excited states is going to depend on how strong are the interactions between the particles. That's given by U naught. So what we're doing systematically is an asymptotic expansion in U naught here. So to the order of accuracy that we're going to work, we're going to say that N naught is just equal to N. I'm not going to really make that much of a distinction. Okay, now in homework, you get to solve the Gross-Pitievsky equation, and you get to derive the energy dispersion relation or the energy spectrum of excitations of the system. So normally we think of the system as being in equilibrium. All the particles are in the ground state, which is the condensate. So there's quantum coherent macroscopic occupation of the ground state. If I excite the system, now I can take those modes and do a Fourier expansion, just as we usually do, a plane wave expansion. Those modes are going to have an excited state given by the wave number k. And the question you want to know the answer to is what is the energy of an excitation that has a wave number k? So in the homework, you get to work that out. Okay, it's fantastic how you can do it. Okay, I walk you through it, and you can all do it. And what you're going to see in the homework is the long wavelength behavior. You're going to see literally the emergence of quantum rigidity coming out of the solution to this problem. Okay, so we're not going to talk about that in class. You're going to work that out for yourself. It's absolutely beautiful. It's fantastic. Now, what I'm going to show you in class is when you do that exercise, what you will find is that if you look at the large wave number behavior of the energy spectrum, what that looks like is basically the free particle kinetic energy, which is just p squared over 2m. There's no interactions. So that's h bar squared, k squared over 2m. And then there's an extra part, which comes from that, which is N naught U naught, and that's like the ground state energy. So if I want to compute what is the total energy of the system, how do I compute the total energy? Well, I set K going to 0 because I'm now looking at the system in the uniform state. Epsilon K, when K goes to 0, turns out to be N naught 0. And how do we work out the energy? Well, I need to work out what the chemical potential is. So I need to work out what is the energy of particles interacting with all the other particles in the system. If I've got one particle here, it interacts with n minus 1 other particles. N is large, so n minus 1 is basically the same. So each particle is interacting with n other particles. Each interaction involves two particles. So when this particle interacts with this particle, that's the same thing as this particle interacting with this particle. I don't want to double count the interaction. So what that means is that the total energy is basically the number of particles, then the number of particles per unit volume times U naught divided by 1/2. And then if I want to compute what the chemical potential is, I take the energy and differentiate it with respect to N, and that gives me N naught U naught. So this is the way that I can work out then what the chemical potential is. Okay, so now what I want to do, we know what this number is in terms of N and U naught. Now I want to know, how do I solve the equation? So because the equation now has, this mu in it over here, so I can divide by mu, and when I divide by mu, then what I'm going to end up with is the equation shown over here on the right-hand side. So here on the right-hand side, the mu is turned into 1, then the factor h bar squared times del squared is now h bar squared 2m divided by n naught u naught, acting on psi. And then on the right-hand side, I have psi naught squared divided by n naught. And remember that the psi naught is r dependent. So the psi naught squared on the right-hand side, absolute value of psi naught squared, doesn't cancel with the n naught, because that's only true for the uniform case. Now this quantity on the left in front of the del squared, I've indicated dimensions of length. How do we know that? Sorry, of length squared. How do we know that? Well, the first term in that equation is 1. All terms in the equation have to have the same dimensions. So since I've got a del squared and del has dimensions of 1 over length squared, that means that this thing must have dimensions of length squared to make sure that the second term is dimensionless. So if it's dimensionless, and I can define it to be a length, so I'm going to call it R naught. So there it is on the right-hand side. And that R naught is then defined by Planck's constant h bar over 2m n naught u naught square root. And that's a length scale. So once I've defined the equation like so, then what I have is an equation now, which is in as reduced form as possible, and that's the one that I've indicated over here on the right-hand side. So now all we have to do, it's pretty simple. We just have to solve a nonlinear partial differential equation, okay, which is a piece of cake. You can work it out asymptotically. You can see the behavior, but I'm going to show you just roughly how we go ahead and do that and show you the numerical solution. So the way we solve this is we're going to use our cylindrical polar coordinates. So we're going to solve it by separation of variables. We know that psi naught, absolute value of psi naught squared, when the system is uniform, just goes to n naught. So we're going to normalize it as the square root of n naught in the front. So that when we take the absolute value squared, you just get n naught. So that's the normalization. And then it's going to have a phase factor. So I'm going to write the phase factor as e to the I phi. And then it's going to have a part that depends on space. And that's going to be a function of the radial distance. So remember, here's my coordinates. So r is the radial distance. And that radial distance, since f has got to be a dimensionless function, must be scaled by the factor r naught. So that's the way we solve this equation. So now, of course, what we do is we make a change of variables. So we simply define a new variable, which is r over r naught, a dimensionless variable. And then once I've done that change of variables and gone and written down del squared in cylindrical polar coordinates, then what I have is the nonlinear equation that you see over here on the right. And this has the boundary condition that f goes to 1 as r goes to infinity, so that well away from the quantum vortex, the wave function of the condensate has the average density as n naught. So we can solve it, and the solution you can prove this for yourself, but I'll just show you the answer. Looks something like the yellow curve over here on the right hand panel. So it has it starts from 0 and rises to 1 as r goes to infinity, and it takes the rise distance, this core size, if you will, is of order r naught. It's like 1 r naught or 2 r naught, something like that. And so that's what the solution of a vortex is. And the fact, so this is the thing that in the past we've drawn like this. So here was our box, and then in the middle was this quantum vortex, which we drew like that, as if it had a complete absence of order. Now we see that that's not really quite true. There isn't an absence of order in the whole core. The order gradually rises from 0 to 1 over a distance of order r naught, and that is the way that we have resolved the structure of this topological defect. Okay, any questions about that calculation? I've gone over it fairly quickly because I'm not really too interested in going through all the details of it, and it's not important that you know them. You've all seen this sort of thing before. I want you to see that you understand what the answer is that we've obtained. Any questions about that? Okay, so let's then move on to the last thing I want to show you, is that this calculation is self-consistent. So how could a calculation like this fail to be self-consistent? So let me draw this over here, and I'm going to come back to the left-hand panel in a second. So let's suppose that this is our system. Okay, and I've got a bunch of particles bouncing around in this box. So here's my particles. So those are my particles bouncing around in the box. I'm going to say that the size of these particles is a radius, which I'm going to call A. So A is equal to the size of the particles, the hardcore radius, and I've got n over v particles as number per unit volume. So you might ask yourself, well, how far apart are these particles? And that's easy to answer. How far apart? Well, we know that there's n over v particles in a volume V. So that means that the volume per particle is equal to V over N. And then that means that the distance per particle, I'm going to assume I'm in 3 dimensions, is then going to be the cube root of V over N, which is N to the minus 1/3. So that's how the distance between particles scales. So why do I care about this? Well, we've used a continuum approximation. Okay, we have this coarse-grained variable psi of r that varies in space, and we'd better make sure that this really is a smoothly varying function. So if it is a smoothly varying function, well, how could it not be a smoothly varying function? So I've got the core of a vortex. So let's draw my vortex sort of like this. Okay, here's my vortex core, like so. It's rotating about this axis, like this. And let's suppose that this scale here is my scale R naught. So basically out here, psi naught is pretty close to 1. And then inside this purple sphere, purple cylinder, the order parameter, the wave function, is going to 0 slowly. So if it's going to go smoothly to 0, then the way it could not do this is if the system actually looked like the picture at the top. If the picture at the top looked like this, and I asked you, is this smooth? Has this got a smooth density? The answer is no. Okay, there's too few particles in the system. So the average distance between the particles is about the same size as the things I'm trying to describe. So that means that the things I'm going to describe is going to strongly fluctuate. So in order for this to be smoothly varying, what we actually need is that there are we need there to be many of the Bose particles in the distance of order R naught, so that psi naught there is smoothly without fluctuations. So let's draw a picture of that. So this is the magnitude of psi naught as a function of R when everything is smooth and everything is self-consistent. If it is not smooth and self-consistent, then this psi would look like this. There'd be too many fluctuations, and so it wouldn't be valid to have this smooth description. So this would be not smooth and not differentiable, and so this would be a breakdown of our coarse-grained long wavelength description. And so these two situations are determined by a very simple condition. Here, there have to be many particles within a distance of order R naught, and here there's only a few particles within a distance of order R naught. And so then I don't have a smoothly varying density, and so I don't have a self-consistent picture. So we started off by assuming this. And if we get this, then we violated our starting assumptions. If we violate our starting assumptions, then that means it's not self-consistent. So, okay, well, how can you tell? I mean, how can we check this? Well, the great thing is that we calculated R naught from the theory. because we calculated from the theory, we can double check. Okay, so let's go ahead and do it. So this is what we have over here on the left-hand side. I'm just going to walk you through it. I did a kind of sneaky trick to show you how it is self-consistent. So if you don't follow it in real time, don't worry about it. But let me just explain this to you. We know that the core size goes like R naught, and this R naught scales like U naught times N naught to the minus a half. We derive that somewhere over here on the left-hand side. So that's how R naught scales. Okay. Now, if I got a weakly interacting gas, how do I get a weakly interacting gas? The usual way is this. The particles, when they collide, they're hardcore particles of radius a. So they'll just crash into each other and scatter. And if they're quantum mechanical, they'll do the quantum mechanical version of scattering, which some of you have done in quantum mechanics. But basically, they're just going to scatter, and there's going to be some big bang, and they'll bounce off each other and go off until they find something else. So in a weakly interacting gas, there's two things that have to happen. One is that the interactions are small, but the interactions can be very strong, but infrequent, and then it will still be overall weakly interacting. So if the interactions are going to be very infrequent, that means that the density is going to be low. So if I've got a low density gas, it's going to more or less behave like an ideal gas, whether it is classical or quantum. As the density goes up, then it's going to have more and more collisions, and I can perturbatively include the effect of those collisions. If the collisions if it's a very high density, then it becomes a very difficult problem to actually be able to compute what the effect of those things is. But our gas is meant to be weakly interacting. So if it's weakly interacting, what does that mean? That means that the distance between the particles has to be much greater than the characteristic dimensions of the particles, because there's no other scale in the problem. So we can check that that's true. So if that is going to be true, then this condition needs to be satisfied. So remember, the distance between the particles goes like 1 over n naught to the 1/3. So that means that 1 over n naught to the 1/3 has to be much bigger than a, and that means that a cubed over n naught, a cubed times n naught is going to be much less than 1. So then if that's the case, then I can make a bound on what R naught is. So I've done the bound over here, and you can check it afterwards. So R naught ends up going as a n naught to the 1/3 to the minus a half times n naught to the minus 1/3. And so I end up with a result that R naught is much greater than n naught to the minus 1/3. So I've shown you from this calculation, because we calculated it, that the core radius is much greater than the mean separation of particles. So what this calculation then tells you is that the mean field theory is self-consistent, and this long wavelength description is okay. And that's the conclusion that we have over here. Okay, so let's go back, let's jump over to this page, to 146. I'm going to just start a new page over here. So you might ask yourself the following question. Could we have actually got a different answer? Okay, are there situations where you do a calculation in some approximation, that the result violates the assumptions. Of the calculation. So in other words, are there situations where you do this sort of exercise that we've just done, and then you find that it doesn't work? And so that's the first question. The second question is, if that happens, is that a good thing or a bad thing? Okay, so let's first of all talk about this. Let's suppose I ask you, if I do a calculation and it's not self-consistent. Okay, so I assume something, do the calculation, at the end, I find that it doesn't agree with the starting assumptions. Is that a good thing or a bad thing? Okay, who thinks it's a bad thing that the calculation failed, that it wasn't self-consistent? You think it's a bad thing? Yeah, you're sensible. Yeah, who else thinks it's a bad thing? Srijit? Yeah. Yeah. Bad. You do a calculation and you think it's a good thing, but the only reason you think it's a good thing is because you know that I'm trying to trick you, right?
No, I think it's because you limit what possible.
Because what?
Because you limit one possibility, and you can try to find it also.
Okay, so you think it might be a good thing because then it tells you that you may have to find another theory.
Yeah.
Okay, yeah, that's definitely that is true. Okay, anybody else have any comments about whether self-consistency is good or bad?
I think maybe the self-consistency is it's just self-consistency. It can't tell the truth is whether it's this theory or not.
Right. Okay. So in the spectrum of truth, we're doing science, so we think we want to do truth. So the one thing is the best thing is to be true and to be absolutely certain it's true. Then the next thing you might say is, well, I don't know if what I'm saying is true, but at least it doesn't violate its own assumptions. So you might say, so self-consistency is, I mean, you on the scale of things that are bad, you think not being self-consistent is like the worst thing. You assume X and then you prove that not X is true. So that's like a theory that's terrible, and EJ wants to go and look for something else. And then you could say, well, I've got a self-consistent theory. At least it doesn't, at least it's not crazy. It doesn't seem to show any problem. And then there's the next question is it actually true? And you're absolutely right. Just because it's self-consistent doesn't mean it's correct. You can be self-consistently wrong. Okay. So let's draw a phase diagram of theories. So I guess this axis here is truth. Okay. So as you said, so over here, okay. So your theory is correct. Let's say over here you might say, well, the theory is not even. Well, actually, I'm going to do it like this. I just realized this. I can make a good joke here. Let me go back to this color. All right. So then I could have over here. So this is sort of like super great. Okay. Then I could have a theory that is, say, in this range, where it is self-consistent. So at least it doesn't contradict its own self. So it's not like you write your paper, send it off to PhysRev, and as you're finishing the paper, you realize the paper's wrong. Okay, it's not as bad as that. Okay, so that's kind of like, yeah, okay, that's okay. But then, of course, it could also be self-consistently wrong. So we don't know what that is. Then you might have the situation over here where it is sometimes self-consistent. Sometimes. Okay. And I think this is great. So I'm going to give this a kind of double star like this. I'm going to tell you why. And then you've got theories over here, which I can't resist doing this. These theories here are not even wrong. Okay, like there's plenty of examples of theories that are not even wrong. Like, I don't know, very very highly hyped theories that are meant to explain quantum gravity and the secrets of the universe, but over the last 35 years have made not a single experimental prediction. I'm not going to say what those theories might be, but you can all think of what you can all imagine what I have in mind. So those theories are, to use Paoli's phrase, not even wrong. Okay, they're not even theories. Now, the truth one, of course, is the best thing, although, of course, you have to really work hard to be sure what you mean by true. This self-consistent thing that is right and that could be right, but it could be self-consistently wrong. So I want to give you an example of that, okay, and why I don't think it's great, okay. And have you all heard of Richard Feynman? Have you heard of Schwinger? Have you heard of Tominaga? No, you have, okay, good. Schwinger, Tominaga, Feynman, they got the Nobel Prize for inventing the normalization of quantum electrodynamics, okay. And then other people, like Tufton Veltman, got the Nobel Prize for showing how non-abelian gauge theories, Yang-Mills theories, are renormalizable. Okay, so what we believed for maybe 50 years, from around about the 1940s, 1945 or so, up to about 1993, was that the theories that are real theories of nature, they have to be theories. They have all the, when you calculate in quantum electrodynamics, you get infinities. Okay, and those infinities mean, wow, the theory is just blown up, it's useless, can't calculate anything. And what people showed, Feynman, Tominaga, and Schwinger showed how you can absorb those infinities into a redefinition of, say, the charge of the electrons or things like that. Okay, so then we can bundle those infinities up into experimentally observable phenomenological parameters, and the infinities have gone away, and now quantum electrodynamics is in fact the most accurate theory that we know. You can make predictions to 10 decimal places, and you can do experiments that test those predictions, and they work. It's absolutely amazing, okay? So those are renormalizable theories, okay? I don't like renormalizable theories. And why don't I like renormalizable theories? I like theories that break down when they tell you when they're not self-consistent. So does anybody have an example of one of these sorts of theories? One that's in the self-consistent sometimes box. Mean field theory. Yes, to say a bit more about that.
So
mean field theory of what?
So like, I don't know, whatever, like the things that we discussed in class, right? Like we have Ising models of like spin systems, and like we saw that it was not consistent below a certain dimension. And then, yeah, like when we compute a correlation function, it just doesn't.
It wasn't. It didn't. They didn't break consistency in terms of. Oh, well, you mean the Ginsburg criterion, like in the phase transitions class? Yes. Okay, that's exactly right. So here I'm going to the example here, my favorite example, because it's to do with phase transitions, is the Landau theory of phase transitions. In the Landau theory of phase transitions, you do an expansion. You look at the interactions, the self-interactions of the order parameter, and what you discover is that that as t goes to tc, so you have a variable which is t minus tc over tc, that variable is getting smaller and smaller, much less than 1, as you go asymptotically towards the critical temperature where there's a phase transition. So you think there's a small parameter in the problem and everything is great. Well, after you do the dimensional analysis on the field theory, and I'm not going to show you this in this class, we did it in last quarter's class. When you do a dimensional analysis on the field theory, what you find is that the rescaled interaction strength scales something like, and I'm probably going to get it wrong, so help me here if I make a mistake with minus signs, something like t minus d minus 4 over 2, something like that. Let's see. So, oh no, I've got it the wrong way around. It's this. Yeah. Let me write it like this. Okay. So So it turns out that this goes like the original one, I'll call it U naught, times this. And you get this by doing dimensional analysis on field theory. And if you want to know how you do that and what that all means, then go and look at the lectures on YouTube for my course, Emergence and Phase Transitions, which I did last quarter. Okay, so this is what you obtain. And what this tells you is something that's absolutely amazing and very important. What it tells you is that as I go towards TC, this parameter little t goes to 0. D is the dimension of space. So if I'm in D less than 4, so like 3 dimensions, for example, then 4 minus 3 is 1. So this goes as t to the minus a half. I'm not confident of this 2 here, but I think it's right. So what that says is that as D is less than 4, the interaction strength U naught goes to infinity. Why does this keep happening? And not 0. So it means that you have a small parameter, but that small parameter is not usable. And why does that matter? Well, when you do perturbation theory in Landau theory, so what you're doing is you're writing the effective Hamiltonian for the system as the integral of grad psi squared plus something like t, a times t times psi squared plus g, plus, I called it u, didn't I? Plus u naught bar psi to the 4th. So that's our Landau theory description. And you would think that you can do perturbation theory about the quadratic terms in terms of the quartic one, but you can't, because the small parameter that you're doing perturbation theory in is large. Once you get below 4 dimensions, and so once you get too close to the critical point, then your perturbation theory breaks down. And this is why the problem of phase transitions was so hard. This is why it took 50 years to solve it, and the person who solved it got the Nobel Prize. And so this is an example of a theory that is self-consistent. Sometimes this theory sows the seeds of its own destruction. You write down Landau theory, and it tells you where it breaks down. And you observe those breakings down, and you can predict them. And what happened, of course, was that people didn't know that. And then they started doing measurements closer and closer to a phase transition, and they discovered that everything goes wrong. And they couldn't understand why, because you couldn't understand even why, in principle, it was possible for this Landau theory to give you the wrong answer. And the story of how that was resolved and so on, that's what I taught last quarter. So it's all there on TV. Okay, so this is why self-consistency is a very important thing, and so self-consistent but is wrong. So and a good example of that would be quantum electrodynamics or any renormalizable field theory. The renormalizable field theories, well, I'm simplifying a bit, so so don't quote me on this, but roughly speaking, the renormalizable field theories never tell you when they're wrong. They always give you a good answer, and you'd have no way to know whether it's right or wrong. Okay, so what happened in the middle 1990s, high energy physics underwent a what do you call it? A phase transition, I suppose. Okay, they all realized that what they were doing was condensed matter physics, but at higher energy scales. So what happened was that people started realizing that what you're doing in high energy physics is effective field theory. It's basically what you're doing in condensed matter physics. You're just doing it at higher energy scales. And if you're interested, you can look on arXiv. Look at a paper I wrote last year for a book called the 50th anniversary, 50 years of the renormalization group. And it's an amazing book, fantastic articles in it. My article in it is all about this effective field theory, and it's a tribute to Michael Fisher, who was one of the famous and very influential originators of phase transition theory and the normalization group in the 20th century. And so all of that story is described there in terms that are not very technical if you're interested to read it. Okay, so we've finished that. And what I want to do now is I want to go on to something completely different. Okay, so let's go on to something completely different. And so what do I want to talk about? So first of all, so this is what we're now going to do is we're going to look at non-equilibrium pattern formation. So what I propose that we do is I want to talk about the following questions. I want to understand why do patterns form? Why do they generically form, in the non-equilibrium systems? And I want to understand when they form, how they form, and what sets the scale of the pattern. And what we're going to talk about, we're going to talk about patterns in space. For the first part, we're not going to talk much about the time dependence. We're going to start off by talking about non-equilibrium systems that are physics systems. And then we're going to switch from that to looking at non-equilibrium pattern formation in some biological systems. So that's the questions that we want to answer. So the reason why we spent the last 5 lectures, the last 5 weeks talking about quantum order and condensed matter physics order is that there's an amazing result, which we'll see. So the amazing result is the same kind of coarse-grained theory that we've used here in equilibrium also applies in these cases. And so we're going to see how that comes about, and we're going to see that by the only real good way to see it is by the normalization group. But there's a quick and dirty way to derive the results from the normalization group, which I will show you, and so it makes a connection with all the themes in this course. And what we're going to see is that we can look at patterns in space. That's what we're going to start off with, and then we're going to look at patterns in time. And then later we'll talk about patterns in space-time. And these are things that might be well worth people talking about for their term essays. I've been looking at. I got some people's essay proposals, so I'm going to be sending you some comments on those. I'm talking with some of you about that. So there's lots of interesting things that one can do here. So let's start by just explaining what the basic question is. So let's give an example of the sort of thing that we're looking at. So I may have a dynamical system that has the following behavior. So here I'm going to draw space, and here I'm going to draw some order parameter, which can be anything that we like. And what we may find is the following picture. Let's suppose that I have a control parameter. And when that control parameter is below some threshold, let's call it epsilon c, then I just have a spatially uniform state. But then when the parameter is greater than a certain threshold, then now I have a state with some periodic pattern like that, with some wavelength, which I'll call lambda, some amplitude, which I'll call A, and this might be true when epsilon is greater than this. And so what we want to understand is what sets the scales of these things. So what is epsilon c? What is lambda as a function of epsilon? What is the amplitude as a function of epsilon? Those are all the things that we would like to understand. And these are all examples of bulk as information. So that means it happens everywhere in the system, more or less the same way. And you can imagine that if I've got these the structure here with an amplitude and a wave and a wavelength and so on, you can imagine that that actually might not be what you see in real life. What you see in real life might actually be some sort of spatial modulation of that, and you'd be right. And we can work out all of the physics of that as well. So that's called bulk pattern information. You have a box, you change a parameter, and then you suddenly make a pattern. But there's other sorts of patterns that I'm not going to have time to spend too much on. So there's other modes of pattern formation. So non-equilibrium systems can have history dependence. Those kinds of things that you see may depend upon its history, because if it's out of equilibrium, that means it hasn't forgot about the initial condition. If it hasn't forgot about the initial condition, then there may be different basins of attraction for different initial conditions, giving rise to different long-time behavior. So there's other modes of pattern formation, and the one that I find the most interesting is a propagating pattern formation. So bulk pattern formation just happens in the interior of something. Propagating pattern formation starts at a boundary and then propagates in and eventually contaminates the system. Okay, so let's so the example that we're going to look at first, and we're going to establish some of the basic techniques, is thermal convection. So let's have a look at it. So I'm going to show you a movie. So all of this is section 7.2 of my ESM notes. So let's go to the. All right. So what did we just see? What we saw was this. I have a system which is heated from below. So I've got a plate here, which is hot. And I've got a plate up at the top, which is cold. And so I'm going to say that the temperature here is equal to T, and the temperature here is equal to T plus delta T. And then what do I have? Well, I have a fluid that's in there, and the fluid is there under gravity. So it's like that. Then the plates, how far apart are they? Well, this is the depth of the fluid. So we'll call that D. And I'm going to set up coordinate axes that look like this. This is X, this is Z, and in this direction is Y. And then, so this is Z equals 0. This is Z equals D. Okay, so what is the cartoon picture? Why do we even have convection at all? So let's talk about the cartoon picture. Okay, so, well, what happens when you heat something up like a fluid? You're saying it goes up. Well, why does it go up? It's what? It gets less dense. Right. Justin is doing chemical engineering, right? That's how he knows all this stuff. And you guys who are physicists don't know. Yes, you heat something up so that delta T is greater than 0, and then the fluid bits near here. So here's a little fluid particle. So the fluid particles, I'll call them people call these things little fluid parcels, coarse-grained volumes of fluid. Let's call them parcels. Expand because of thermal expansivity. So they expand, and that means that their density goes down. And then why do they rise? You said that the things go up. Why do they rise? So I'm trying to just sort of narrow down approximate cause for the phenomenon that we just saw in the video. Okay, somebody else? Why do they rise then?
That's lower. That's the light up top.
Right. So it is, but the word for that is buoyancy. Okay. So since its density is lower, a little hot spot has lower density than the fluid around it, then by Archimedes' principle and so on, it's going to experience a force and goes up. So that means its density will go down, and that implies that it will then be buoyant, and that means it will experience a force that pushes it up. Okay, so that's the basic idea. Okay, so then you say, well, okay, fine. Well, why, all the fluid is heated below, so it's all trying to go up, but it doesn't all just take off. It's still there. So what? So this is part of the story, but there are opposing forces. Okay, there exist opposing forces. So let's ask ourselves what the opposing force is. So what is the obvious thing that is going to stop the fluid from moving? Somebody else. What you said that it will, as it goes up, it will cool down, and then the force will stop being so strong, and so that's true. That's true, and we will come to that. But even just at the beginning, just when you're just starting to get it moving, what is there that's going to try to stop these little bits of fluid going up? Gravity is trying to push it. Well, gravity is really why it's going up, right? Right? Gravity is pointing down, but making it go up. Okay, but what's trying to oppose it? Viscosity, exactly. So the opposing force is viscosity. The fluid is viscous. And so as this thing is trying to move, it feels a drag from the fluid around it. It's like a little bubble, if you want, that is moving through a liquid. The bubble doesn't move at infinite speed. It feels a drag force on it. And so viscosity opposes that. And so we expect that the friction is going to be something that is going to make is going to stop it. So far, what we've said is that that the variables that we need let's just see what we have so far. So we have viscosity, which is sort of opposing. and then pushing, as it were. Well, we have the thermal expansion. Which we'll call alpha, so that's one force. And then we've got the fluid density as a function of temperature, so that's going up like that. We sort of have G here for the reason that we said. So that's our description. Can anybody think of there's one more variable that we haven't talked about that needs to be talked about, and that needs to be added to this set of variables that describe the problem. It's kind of related to what you were saying. Okay, but you were talking about it once it gets to the top. This is something that happens right near the bottom. There's one more effect. So say it again. Heat conduction coefficient, you mean? Yes, you're right. Why? Well, what does that do?
Because when heat flows, it affects how much heat flows when it goes up.
You're still thinking about it moving up. I want you to think about it, or just staying down here at the bottom. Okay, your answer is correct, actually. Okay. Think about this. Suppose I heat up this little packet of fluid. Okay, but let's suppose there is a high thermal conductivity, which is, I think, what you were saying as your answer. If there's a very high thermal conductivity, what will happen when I heat up this little packet of fluid? It will cool down very quickly, and then it won't. So that'll goes out like that, and then that little packet won't rise because all the excess heat got taken away. If, on the other hand, thermal conductivity was very small, and this packet is being heated up somehow by some fluctuation, and now it's going to keep that heat, and so it's going to keep rising. And as long as it keeps that heat, and it's higher than the surrounding medium, it's going to keep on experiencing the buoyancy force. So you're absolutely right. So there's another thing that comes in here, which is kappa, which is the thermal conductivity. And so let's just write that down. So the thermal conductivity being small, that means that the hot fluid parcel stays hotter than its surroundings, I guess. And then it'll be buoyant for a long period of time. So those are some of the factors that that will be important. So now we can ask ourselves, what does the phase diagram look like? Now, you're not seeing convection all the time, because you've just told me that if the buoyancy force is not strong enough compared to the thermal conductivity and the viscosity, then it probably isn't going to move. So think about it like this. If I've got delta T over T is very much smaller than 1, then what's going to happen is that the heat will diffuse from the bottom to the top just by regular diffusion, by conductivity, but the fluid isn't going to actually move itself because, let's say, the buoyancy force is too weak, so the viscosity will hold it back. And so the heat will diffuse from the bottom to the top, and the fluid will not move because delta T is too small to overcome the viscosity and perhaps the thermal conductivity as well. So that's what's going to happen. Then you might say, well, then there's another phase where this delta T is larger. So let's just say delta T is some fairly big number compared to the actual temperature at the bottom. So then what's going to happen is the fluid will go into motion. And will transport heat faster. More efficiently than in the first phase. So it's going to do that, but and so that's good. That's the basic phenomenon. And you might ask, well, how is it going to form a pattern? Well, the problem is this. There's a problem. All the fluid cannot go up and levitate. Okay, the density, mass is conserved and so on. And so what it does is it self-organizes into a pattern. And what that pattern looks like from the side is the side view of the pattern. So here again is my hot bottom plate. Here is my cold blue plate. And then what the fluid ends up doing is it makes a pattern like this. The fluid over here, let's say, starts to go up, comes to the top, and then comes down like this. And then the fluid over here also comes down. The fluid flow has to be continuous, so it's going to go down like that, and then come up like that, and then like so, and so on. And so that's an example of a pattern, and these things have the name, they're called rolls. Okay, so those are rolls, and we want to understand what is the spacing and how fast do they move, and so on. So this is so they have to do this because the fluid can't all go up. The fluid has a conservation law. So if it's going to go up over here, it's got to go down over here so that the overall density doesn't change much. So if we now look at the pattern, if we look on the side view, so the pattern is going to look something like this. So let me draw it like that. So this is the top plate. This is the bottom plate like that. So this one is hot. And the top one is cold. And then I've got these rolls that are in the middle. So I've drawn these things like this. And then what they are, they're going to line up into sort of sausages going in this direction, and they're going round like this, and so on. And you saw in the video, and I'm not going to risk showing the video again. You saw in the video that the miso soup came up in the middle of those cells and then came down on the outside, and so you could see there was this motion like that. So this is one possible side view. Another kind of side view that you could have is, let's suppose I look at it from the top. So there you've got these rolls, but you could get something like this. And I've got these patterns, which are roughly hexagonal. Of course, I'm not going to draw them very well. Something like that. So you get these hexagons, and what's happening there is that in the middle, of them, the fluid is coming up, and then on the edges, it's going down. So I'm trying to represent that like so. And that's what we saw with the miso soup. So that's the top view. So this is a hexagonal convection pattern. And you don't just have to see it in miso soup. You can go to places like the Giant's Causeway in Ireland, and you can see these beautiful basalt formations where you see the rocks actually form these hexagonal patterns. You can look at drying patterns in salt lakes and in Utah and the Dead Sea and other places. You see these hexagonal patterns all over the place, not just in convection, actually in all sorts of other things too. In fact, there's a generic Landau theory reason why you see hexagons, why you see that. It all comes down to symmetry, and it's amazing. So this pattern here, this hexagonal one, is a generic pattern, and these are stripes. It's also a generic pattern. And then you can ask, how do these patterns make transitions between themselves? They do it through a huge number of mechanisms. I'm going to show you just some of the mechanisms in this class, but not today. So we're nearly finished. I'm going to finish here. So next time, what we're going to do is we're going to make a minimal model for this convection. And we're going to get a whole set of coupled partial differential equations. I'm going to show you how we can solve them. And we can classify, work out the phase diagram of this non-equilibrium system and work out when we get patterns, when we don't, and what is the stability of those patterns. Okay, so I'm going to finish